Okay, section 3 is over motion in space, and we're going to look specifically at Kepler. And so to start off the section, you don't have to make a sketch, but think about the path of the Earth as it orbits the Sun. Think about what it looks like and kind of describe the motion of the Earth as it follows that path. And what similarities and differences are the path of the Earth and that of other planets. So just think through those for a second. Okay, and then we also will talk about what weightless means to you. So think about if we say something's weightless in space, we say that you are weightless. What does that mean? Have you ever observed someone in a weightless environment? How does their weightless environment differ from their normal environment? So Johannes Kepler built his ideas on planetary motion using the work of specifically Copernicus and Brahe. So that he came up with these three laws: that each planet travels in an elliptical orbit, so it is not a circular orbit, it is an ellipse, an elliptical orbit around the sun, and the sun is one of the focal points. The second law is an imaginary line drawn from the sun to any planet sweeps out equal areas of time, or equal areas in equal time intervals, which means when you are closer to the sun, you have to go through it a little faster. The third law is the square of a planet's orbital period is proportional to the cube of its average distance between the planet and the sun, or T. So big T is period, which is the time for one orbit. T squared is this little symbol is a proportionality symbol, so we will use some constants and other variables to make that an equality. But right now we're just saying as t goes up, the square of t goes up at the same rate as r cubed. So his first law: orbits are elliptical, not circular. Some orbits are only slightly elliptical, so the amount of elliptical properties it has is different. His second law states that equal areas are swept out in equal time period intervals. Okay, so this is, well, first of all, this is what an ellipse, in case you didn't know what an ellipse is. It's an elongated circle. So here the planet would be farther away from the sun than at this part of their orbit. For Kepler's second law, equal areas are swept out in equal time periods. So this area of the circle versus this area is equal. But look at the arc that it has to travel. It has to travel a lot longer arc length in this area than it does in this area. So, but the same time period occurs, which means you're going to be moving faster around the sun in this time period, this distance, than out here. And his third law relates the orbital period to the distance from the sun. So the period of time, a period is the time for one revolution around the sun. As distance increases, the period increases, but it's not a direct proportion. So t squared over r cubed has the same value for any object orbiting the sun. So we can use that to calculate the period and such. So here is, okay, remember I said that that little symbol was proportionality. Now this isn't t squared, but look what they've done. We have a square root. So if we wanted this to be t squared, it is directly proportional to r cubed if we squared both sides. So t squared is still proportional to r cubed, even though t squared is not in this equation. It's because we have this radical sign. So t is equal to, the period is equal to 2 pi times the square root of r cubed over g. G is that same constant, the universal gravitational constant, times m, the mass of the central object. Okay, we can also, because period is proportional to velocity, we can show this equation in terms of velocity, not just period, is equal to the square root of g times m over r. The mass of now this is always the mass of the central object. And then the mean radius, so the average radius. So orbital period and orbital speed. Using SI units, so prove that the units are consistent for each equation shown above. Well, let's look. Get my pen ready here. Looking at just units, we have r cubed. So r should be in meters, and that will be meters cubed over, okay, so what was it, a Newton times meters squared over kilogram squared, right? That should be the units for G always. And then times M, so that would be times, mass, not a kilogram. So now let's look at what the units, and we're going to take the square root of all this actually. Okay, so one of these kilograms cancel. Meters cubed cancels out 1, so now we're left with the square root of a meter over a Newton over kilogram. Now what's a Newton? A Newton is a kilogram times meters per second squared, right? And then this is all over a kilogram right here, and there's a mass over all of that. So we have this. So the kilograms will actually cancel out. Meters will cancel out. And now since we have in the denominator, we have a second squared in the denominator, this is actually equal to just the square root of a second squared, which that will equal second, which gives us our units for period. Period should be in seconds. What about speed? We should get meters per second for speed. Let's see if we can do that. So we have the square root. Our units for G is n times meters squared over kilograms squared. And then we're taking it times mass of kilogram over radius is meters. So right away, one of these kilograms cancel out. It's not squared anymore. Same with meters. Okay, so now we have a Newton times a meter over kilogram. And we said a Newton is a kilogram meters per second squared. And then we're going to times it by a meter over kilogram. There we go. Missed my spot. Meter over kilogram right here. So the kilogram, the other kilogram is going to cancel out. And now we have the square root of a meter squared over a second squared, which is going to give us just meters per second, which is what we need for speed. Right? So we do have the right units. That will give us the right units. So a large planet orbiting a distant star is discovered. The planet's orbit is nearly circular and close to the star. The orbital distance is 7.5 times 10 to the 10th meters, and its period is 105.5 days. Calculate the mass of the star. So what do we know? We know orbital distance. So that would be r. So r is going to equal 7.50 times 10 to the 10th meter. The period, so that's t, is equal to 105.5. Now this is days, so we know, we just calculated our units for period need to be seconds in order to fit in. So we're going to have to do a little conversion. what do we have? There's 365 days. Oh, well, I'm not going to years. I want to go to seconds. In one day, there is 24 hours. In 1 hour, there is 60 minutes. And in 1 minute, there are 60 seconds. So I have 9.12 times 10 to the 6th seconds. And then we want to know what mass is. Okay, so we're going to use our period equation. Let me write that out. Our period is equal to 2 pi times the square root of r cubed over gm. So our period is 9.12 times 10 to the 6th seconds equal to 2 pi times the square root of r is 7.50 times 10 to the 10th, but we're going to take that and cube it over, okay, the constant for g is 6.673 times 10 to the negative 11th, and then times m. So we got to solve for m. Go ahead and take a little bit of time, pause it if you need to. We should get an answer of 3.00 times 10 to the 30th kilogram. Okay, and then the next one is, what's the velocity of this planet as it orbits the star? So our equation for velocity is square root of g, which is still at 6.673 times 10 to the negative 11th, times m over r. So go ahead and plug your numbers in for that, and you should get, let's see, 5.17 times 10 to the 4th. So go ahead and pause and work that out if need be. Okay, the next part of this chapter, or this section, is weight and weightlessness. So think about if you're standing on a bathroom scale, the scale measures the downward force exerted on it. Now, we've kind of done some of these examples already last semester, where we think about how our apparent weight can change based on if there's extra force up or down on ourselves. The readings will change if someone pushes up or lifts down. Your scale reads the normal force acting on you. So that's your apparent weight is your normal force. So here is in an elevator, if you're just standing there, the normal force is equal to the gravitational force. Okay, we're accelerating downward, and that means that your apparent weight is going to be less than your actual weight, because basically you are being lifted up because you're not going down as fast as the elevator. If their acceleration downward was equal to g, so you're in free fall, because your acceleration is down at equal to g, you now have a normal force of 0. So because it no longer is supporting your weight, you are no longer having any of your weight actually pushing down on it. So that's really what weightlessness is. So you're falling at the same rate as your surroundings. There's no support force from the floor. So in astronauts in orbit, they are actually falling towards the surface of the Earth at the same rate as their capsule or their spaceship or whatever they're in. So that's why they appear weightless. So true weightlessness only occurs at great distances from any mass. So when you're in orbit around the Earth, it's an apparent weightless, not a true weightlessness. So think about, well, the simulator that they use, they have the vomit comet, they call it. It's because when they train astronauts to get ready for that weightless environment, because it is so different and it's so different on your body, they take you up in a jet very high, and what they do is they basically take a nosedive so that the jet is falling at the speed of gravity, which means you are now weightless. You are floating inside of that jet, and that's how they practice their weightlessness. It makes a lot of people really sick. That's why they call it the vomit comet. And actually, without that gravitational pull or needing to work against anything as they're in space, because they have that apparent weightlessness for a lot longer than in that simulator, your muscles really start to atrophy. You have to, it's because there's no gravity. You're not really working, everything is weightless around you. You are not working against gravity for anything. So that's why astronauts really can't be out in space for that long. It's hard on your body. So not only do your muscles atrophy, that tension of your muscles on your bones is what keep your bones strong. So your bones actually start becoming weaker. And so it just deteriorates your body. Your body needs that resistance to be strong. So now as we go back through these questions, we should know that the path of the Earth is an ellipse. And every planet is an ellipse that just might be a little differently shaped. The amount of elliptical shape it has would be different between the different planets. The term weightless, what does it mean to you now? Has your definition changed? And have we ever really observed someone in a weightless environment? Probably not, unless you've been watching a video. And so you should now know how their weightless environment differs from a normal environment based on their